In this video, I want to talk about implicit differentiation. But to start off with, I just want to work an example without knowing anything about implicit differentiation. So we'll work this example only using things we know right now. And at the end of the video, we're going to come back to it and talk about it in terms of implicit differentiation. I'm asked to find a tangent line to x squared plus y squared equals 4. This circle of radius 2 centered at the origin at the point square root of 2 comma square root of 2. This point right there. So what I'm thinking, everything I know about derivatives right now are about taking the derivative of functions, y equals f of x. So I need to talk about the top half of this circle as a function. So let's solve for y. Taking x squared away from both sides would get me here, and then taking the square root of both sides would actually give me two equations. Y is plus or minus the square root of 4 minus x squared. The plus is talking about the top half, the minus would be talking about the bottom half. So for our problem, I just need to be taking the derivative of the top. For convenience sake, instead of using the square root, I'm going to think of that as a 1/2 power. And I'm going to take that derivative using the power rule and the chain rule. Multiply down to 1/2. Take 1 away, multiply by the derivative of the inside. And I'm going to rewrite that. The 2's would cancel. I'll be left with a minus x over the square root of 4 minus x squared. Now we can go and find our slope. Y prime of the square root of 2. So on top I would have minus root 2, and on the bottom I would have the square root of 4 minus square root of 2 squared is 2. So let's see, that's minus root 2 over positive root 2 is minus 1. My tangent line has a slope of minus 1 and passes through this point. Using point slope, I can find the tangent line. Oh, let's see, y minus root 2 equals minus x plus root 2. Add root 2 to both sides, and my tangent line will be y equals minus x plus 2 times the square root of 2. 2 times the square root of 2 would be about 2.8. So if I looked at my graph and I drew this tangent line, it would have a slope of minus 1. It would hit my y-axis up there at the 2 times square root of 2 value of about 2.8. So I've been able to do this problem, and I've just been able to do it completely using the language of functions. So I want to pause here, and I found my tangent line, and I hope to do this problem again using what we call implicit differentiation. But before we get started, let's just look at a derivative of an expression. Let's say u is a differentiable function on x, and someone has asked us to write down the derivative of x squared plus u squared. Well, the derivative of x squared is 2x, and the derivative of u squared would be 2u times the derivative of u with respect to x, using the chain rule, right? That's the chain power rule. Well, let's do another one like this, but I'm going to write it down just a little bit differently. Instead of u being a differentiable function on x, I want to think about y hiding a differentiable function on x. And now I'm going to take the derivative of, let's say, 2x to the 5th plus y cubed. Now when I take the derivative, I still have to be thinking about the chain rule. It's just that y is very secretly a function on x. So I take the derivative, 10x to the 4th plus, and then 3y squared, but I'm not done because I have to multiply by the derivative of the inside function, because y was a differentiable function on x. And this is actually going to give us all the tools necessary to differentiate implicitly. The method of implicit differentiation is this. One, we're going to differentiate both sides of an equation. With respect to x. Treating y as a differentiable function on x. So every time I see a y, I'll have to remember the chain rule and say times dy dx. 2, we'll collect all of the terms with a dy dx in them. On one side of the equation. And then finally, we're going to solve for dy dx. That will give us an equation for the first derivative, but it will be in terms of both x and y. This is where I want to go back around to our circle example. With the instructions just to be find dy dx, find the derivative. Well, we know we could rewrite this as a function, but let's use implicit differentiation, where the instructions are to simply take the derivative of both sides with respect to x, treating y as a differentiable function on x. So I need to take those two derivatives. That reminds me of what we did here. The derivative of x squared plus u squared was 2x plus 2u times du dx. And what I realize now is it wouldn't have mattered if I called this y. It would have made this a y and then 2y times dy dx. The only thing that's important is that this variable y is a function on x. So let's take this derivative. The derivative of the left-hand side is 2x plus 2y times dy dx. The derivative of 4 is 0, because the derivative of a constant is always 0. All right, I'm supposed to solve this equation for dy dx. So let's get the dy dx on a side by itself. So we'll just take the 2x away. That's going to give me 2y is equal, 2y dy dx is equal to minus 2x. Now we have to divide both sides by 2y. That's nice because the 2's cancel, and it gives me dy dx is equal to minus x over y. This is a formula for the first derivative where I have to know both an x and a y. We started off wondering about a tangent line at root 2 over 2 comma root 2 over 2. Well, if I plug that in, I'll definitely get a slope of minus 1. Notationally, if I'm plugging a point in, what I do is write that down like this. And that's the same slope I got before, so I'm going to get the same tangent line. Going back to our original work, here's my equation for y prime, minus x over the square root of 4 minus x squared. And I realize that on the top half, that's the value of y. That says minus x over y. We actually got the same equation, and I feel like we had to do a little less work. Implicit differentiation here has this big advantage sometimes of really shortcutting the work. But more importantly than that, this formula works for the entire circle, not just the top half. The formula on the other board only works for the top half because the values of y on the top are positive and the ones on the bottom are negative. This formula takes that into account. All right, that's the basics of implicit differentiation. There are more examples to come.